Hi, welcome back again, and in this video we are going to talk about rolling motion on an inclined plane. Now I'm going to talk about this particular thing as a problem, not as a concept, because there is nothing new that I'm going to teach you, and there is nothing new that anybody teaches you. So rolling on inclined is not a new concept, all right? Whatever we have learned before. So I'll just quickly summarize all the things that we have learned before. We have learned that whenever there is rolling, there are two things: rotation and translation, right? You have to deal them separately. Dealing with one, forget about the other. Any answer, always solve by rotation, translation first and then rotation first, or the order depends on you. You can do rotation first and translation first. That doesn't matter at all. And the third thing that we need told you is that take care of slipping. Whenever there is rolling with slipping, it means that the 2 points in contact, they have different velocities or different accelerations, right? And if there is pure rolling, which means that rolling without slipping, it means that both the points must have same acceleration and same velocities as well. All right. So now rolling on incline, as I told you, no new concept. We are going to apply the same thing, and I'm going to show you the power of these general. As I always tell, that the concepts are few, and that's why physics, or in fact the whole science, is very beautiful, because it has certain understandings, certain rules that are few, that are small. See, F equals to ma is such a small equation. I always tell about that. So that's what we are going to apply, and we are going to see that how rolling on any kind of rolling on incline problem is going to be very easy after that. All right. So let me take one example. So this is here an inclined plane in front of me. Let's say it is inclined with an inclination theta. All right. I'm just taking everything in terms of variables. Then let's say this is some object which is rolling here. I'll just okay, I'll draw it nicely. So give me a moment. All right, so I'll draw again. This is the inclined plane with some inclination theta, and there is something which is rolling here. And I've left some gap between again these two. See, it is rolling, it means of course they are in contact, and I have left the gap because I have to draw arrows here and write values so that the diagram doesn't get cluttered. That's why I have left that gap here, okay? So that should not be a point of confusion at all. Alright, so let's say its mass is m and its moment of inertia is I, and let's take the same problem like we have been doing from last two episodes, that if we have to find out because it is rolling, it will have some translational acceleration A. It is also translating and it is also rotating, right? You can visualize whenever these two things get combined, the net effect is rolling. So it will be rotating and falling down, rotating and falling down. You can always visualize it in two parts. First part, forget rotation. It is only just sliding. Second part, forget it is sliding. It is just fixed about this point and rotating here. When you combine this, you get this both kind of motion. That's simple to visualize and understand. Alright, now let's say that again this incline has to be a rough incline, because if it is not a rough incline, the rolling will not be possible. If it is not a rough incline, it means that what's happening is that there is going to be no friction here at all, and you know that there is going to be some mg sine theta force acting on it, and that mg sine theta force will always act from the center of mass. All right, so this is our problem. This rolling object, we have to find its translational acceleration A and angular acceleration alpha. All right, so I'll redraw the diagram. Okay, so this rolling object, we have to find its alpha and we have to find its acceleration A. And tell me, here mg sine theta force will be acting on it, alright? And if this is rolling without slipping, again, what is the thing that we need to remember here? So we need to remember that if it is rolling without slipping, then these 2 points, the point of this incline and the point which is touching the incline, these 2 points must have always what? These 2 points always must have same acceleration. And not only that, because it is not slipping, there is static friction. And again, like we did in the previous two problems, if there is static friction, we again don't know its value. See, static friction can be anything from 0 to mu n. I have been repeating this again and again. So if static friction can be anything from 0 to mu n, then again we don't know the value of friction, so we also don't know its direction. We don't know in what direction friction is actually acting. So you can assume any direction. I'll just take it. If you want, you can take the friction forward. If you want, you can take the friction backward. Whatever, because it's variable anyways. So when you will solve at the end, you are anyways going to get the answer. So what I'm going to do here is that I'm going to take the friction forward. Let's say I've just assumed, and this friction is another variable that I have in front of me. And those people who have been following last two videos, they will find this problem again very simple. How many variables? 1, 2, and friction as third variable. How many equations we can write? First equation we can write by translation, second equation we can write by rotation, and third equation will come from no slip condition. That is as simple as it is. Okay, so first of all, let's break this motion and consider the two parts. So here, let's say it is only translating, as I told you, it is only coming down with an acceleration A, alright, and the force acting is mg sine theta here, and the force that is acting here is the force of friction. So there are two forces acting along this direction. So what is going to be the equation? Mg sine theta minus F is equal to ma, right? Its mass is m, moment of inertia is I, as given in the problem. So what equation I'm going to write is that mg sine theta. Okay, so I have taken friction in forward direction, sorry. So I have taken friction to be in forward direction. So we'll go with that. So both forces in the same direction. So mg sine theta plus F. So mg sine theta plus F is equal to ma. This is our first equation. Now second case, I'm going to consider this object only to be rotating with some angular acceleration alpha. And again, two forces, mg sine theta, forces remain same. Nothing changes with the force. And it is rotating about the center of mass. Tell me, what is the torque of mg sine theta about center of mass? 0. Because, and you know that the equation for pure rotation is net torque is I alpha. Like equation for translation is net force is mass into acceleration. Similarly, equation for angular acceleration is net torque is equal to I alpha. So what is net torque? So mg sine theta, the torque of mg sine theta is going to be 0. What is going to be the torque of friction here? This is R. So the torque of friction is going to be in this direction. Now see, the torque of friction is going to be here anti-clockwise, alright, which is opposite as the sense of alpha. So you have to take care. If let's take clockwise to be positive, so anti-clockwise is automatically negative. If you take anti-clockwise positive, anything which is clockwise is going to be negative. So this is totally your choice. I am taking clockwise to be positive. So anything anti-clockwise is going to be negative. So what is net torque here? Net torque is only Fr, and that is going to be a negative torque because that is anti-clockwise. So minus Fr is equal to I alpha. Alpha is positive, so I have clockwise, so I wrote it as positive. So this is again the second equation. And what is going to be the third equation? Because we have three variables, we need one more equation, and we know that the third equation comes from the no slip condition. The third information that we have, that this rolling object is pure rolling. It means whatever is the acceleration of this point, same is the acceleration of this point. And this is a fixed incline. So whatever is what is the acceleration of this point? The acceleration of this point is nothing but 0. Alright, this is 0. And what is the acceleration of this point? To find out the acceleration of this point, you know that this again, think from translation. If it is only translating with acceleration A, due to only translation, what is the acceleration of this point? The acceleration of this point is going to be also what? A only. Alright? And only due to rotation. See, when it is only rotating about its center of mass alpha here, what is going to be the, if it is just rotating here, not moving. See, we are dealing separately. You understand that, right? Okay, so here if it is R, you know that here it is going to be alpha R. So A is in this direction, alpha is in this direction. So net acceleration of this bottommost point is actually going to be A minus alpha R. So, and this point's acceleration must be equal to this point's acceleration. So A minus alpha R is going to be equal to 0. Three variables, three equations, guys. Again, it's maths. And as I told you, sometimes, most of the times in problems, they will ask you what is the value of friction. Or they are actually, what they do is that, if you see IIT problems also, or some trivial problems in some books, you will find out that they will give you disk, sphere and all these things, and they will ask you who is going to come fast. So what now you have to do is that I have taken any rolling object with some general moment of inertia I, right? If it's a disk, you just plug in the value of I. If it's a sphere, again it will have a different I. So the value of I will be different for disk, sphere, ring, or whatever. And after solving all these three equations, you can get the value of A, right? Now, I am not going to do this because this is math. Three equations, three variables. This is purely math. You will get A equals to something, right? Of course, you can solve this. This is the solvable equation. This is a solvable system of equations. So once you get the value of A, you can figure out the A will come something in terms of I, moment of inertia and all, and after plugging in the value of I, you can check that if it is a disk, what is going to be the acceleration, if it is a sphere, what is going to be the acceleration, if it's a ring, what is going to be the acceleration, if it's a cylinder, what's going to be the acceleration, and you can always compare that in which case the acceleration is going to be maximum. Now, try solving the same problem when this disk is rolling upwards. Try writing the same three equations, and again, have confidence. There is going to be nothing else. You have to follow the same strategy, and you have to again write for translation, then write for rotation, then write for no slip. You are going to get the same three set of equations, and you can solve and get the answer. Always remember, whenever pure rolling, we don't know friction, assume friction. You can take whatever direction of friction. See, I have assumed the direction of friction to be forward here. If in my final answer, the friction appears to be negative, it means that my assumption is wrong and it is in backward. If the final value of friction comes to be positive, it means that my assumption is correct and friction is forward. That's all. That's how you can solve any rolling on incline problem. Thank you. Have a nice day.